Welcome to Data Science 1, Probability, Poisson Experiments. All right, so in order to understand this video, you're going to need to go back and make sure you understand what permutations are. They're going to show up in the formula. You're going to need to know what a probability distribution is, and yes, a Bernoulli experiment. We're doing Bernoulli experiments again because we love them. All right, a Poisson experiment is one where we count the number of Bernoulli outcomes that occur over a specified amount of time or space. Okay, so before we actually ran a trial to see what happened. Here we're not running a trial to see what happens. We're simply observing without intervention. So this will be clear once we see what happens on these. But the amount of time that we use in our time interval is specified by us. So let's look at some examples. The number of customers who come to a sales stall per day. Notice the per day. You see the time in this random variable. And notice it also says number of. So whenever you hear number of per day or count per day or count over time, you're going to have a Poisson type of experiment, most likely. Number of fish caught per day. Number of cars that drive through an intersection per hour. The number of website hits per minute. The number of defects in fabrics per meter, because it can be space as well. Just doesn't need to be time. Now, notice that we're counting again, so we can only have whole numbers, okay? And also notice that time and space is a continuous measurement versus a discrete measurement. Okay, so here is the PDF for this, or the probability distribution function. Now, I'm not going to explain where this comes from just because it takes a whole bunch of time, and we don't really need to know where it comes from for right now. So notice we have lambda to the x. Now, lambda is the mean or expected number of observations or Bernoulli outcomes in that time interval. So lambda to the x, e, which is Euler's e, to the negative lambda over x factorial. So our factorial buddy shows up again. Okay, so again, x is defined over whole numbers, but lambda, since it's a mean number or an expected number, it's got to be greater than 0 because we can't expect negative things to happen when we're counting them. Okay, so, and it also doesn't need to be a number that we actually can observe because it's a mean. Okay, it's kind of a balancing point. We'll talk about those more later, but just keep in mind that it just has to be greater than 0. Okay, so here's a quick example. Maria is selling apples. She wants to know how much she's going to sell this Friday. Why? Why would I want to know that? Well, if I'm selling apples, I want to know how many to bring, right? If I'm selling lots of apples, I want to bring lots of apples. But if I'm not selling a whole lot of them, I don't want to bring a whole bunch of them. So this gives her ability to look at the probability that she'll sell a certain amount of apples. So here, let's suppose she sells exactly 23. Now, the mean number that she sells is 19.3. So we just have our formula from before, plug everything in, lambda to the x, e to the negative lambda over x factorial, shove that in, 19.3 to the 23rd. Wow, that's a big number. E to the negative 19.3. Wow, that's a small number. Okay. And in the denominator, 23 factorial, which is a big number. And when you put all this together, you end up with about 5 to 6%. So there's about a 0.059 probability that she'll sell exactly 23 apples. Not at least, not more than. That's exactly what she would sell. Okay, so Poisson experiment and its associated random variable and probability distribution are a little more complex because we're not intervening to make something happen. Okay, the sample space is really large. The random variable is just, some count over some time or space, and it allows us to find probabilities in this really complex space. Now, we'll look at the properties of this type of experiment later, but I'm just introducing it now. So we'll see you in the next video.